Hi everybody. It is time to talk about a little bit more about Newton's laws. Today isn't so much about principles as it is about application of those laws, and that's what the rest of this unit is about. We'll talk about equilibrium, we'll also talk about non-equilibrium situations. We'll do 4 problems from the book. So you want to either take out your textbook or you want to get your little, what color is that? Goldenrod booklet. That's what we're looking for, a little goldenrod action. So if you can find those, that would be great. Just pause right now. You're back from getting your book. That's terrific. Glad you were able to do that. We're going to talk a little bit about, like I said, about equilibrium. Sorry. And what I mean by equilibrium is that the sum of the forces is equal to 0. So that means that if you add up all the x forces, that's going to be 0. If you add up all the y forces, that's going to be 0. Now you'll find that I tend to put everything on the x, y scale. I call everything that goes this way and this way are positive for me, and any force that goes this way and this way are negative for me. That's not the only way that you can do these problems. I mean, it's possible that you can think that out beforehand and just subtract them whatever way you need to subtract them. It doesn't really matter that much. What matters is that you have them, is that you have a consistent system that you're able to use to figure out the problems. Okay, well, we're going to do an equilibrium problem now. The one we're going to do is actually on page 173. And it is number 61. Sorry, 5.61. Okay. And what we're going to do, if you look at the picture, it shows a cable that's like, or 2 cables attached to a ceiling. And that one of them is at 60 degrees. One of them is at 40 degrees, and it's holding up an object here. And first they tell us that, first they ask us to draw a free body diagram of all the forces on the knot, this thing right here. Well, that's pretty easy. I mean, there's going to be an upward force from this tension, and there's going to be another upward force from this tension. And again, if you want to be technical, there's a third rope from, or a third tension from here, but that third tension is going to equal the weight of the box. Either way is fine. It doesn't matter that much. Okay. The key is here that nothing is moving, so we know that the sum of all the forces is going to equal 0. Now they tell us that the maximum tension, first they ask which is going to have the greater tension. Well, that's a good question. If you look, this one here is holding more straight up than that one is. Or the T1 is holding straight upward, is holding a little more straight upward than this one is. And it turns out that in that case, T1 is going to be greater than T2, because it's going to have its it's going to have that horizontal force spread across more of the rope for T2, which is going to actually lead to a smaller tension overall. And because this one is actually closer to straight up and down, it's going to actually have it's going to actually hold it up with a greater amount. That's how, whenever they're unequal ropes, the one that's closer to vertical is going to give you a greater tension. They also say that neither rope, that's part A, they say that neither rope can hold more. That T1 cannot exceed, it has to be less than or equal to 5,000 newtons. Same with T2. But who cares? I mean, this is going to be the bigger one. It's going to get to there first. Okay. So, we're going to plug in 5,000 newtons. Sorry, 5,000 newtons for T1. And we're going to solve for mg. Because I asked what's the greatest mass, I think. Yeah, say the maximum value of the hanging weight, so we can just find mg. It's no big deal. Okay. So what we're going to do is first we're going to go to our force diagram back here, free body diagram, and I'm going to recopy it because technically we have a bunch of different forces. Or we should say, we have T1, T2, and mg. You can see mg acts only in the y direction, but T1 is going to act in negative x and negative y. No, I'm sorry, positive y, because it's going to pull up. I can make a plus sign, really. Okay, and this is going to act in positive x and positive y, because it's going to pull up and to the right. So, what that means for us is that we're going to have to add all the x forces and set them equal to 0. I'm going to have to add all the y forces and set them equal to 0. Now what that means is that we're going to have T1, because that pulls to the left, so I'm going to call that minus T1x, and plus T2x equals 0. Those are the only two horizontal forces. If we go back to our picture, the mg only pulls vertically. So here we're going to have T1y plus T2y minus mg equals 0. And that makes sense because this is pulling up, this is pulling up, this is pulling down. So now we got to use our angles. And because our angles are to the horizontal, we can just say cosine is x and sine is y like we did with projectiles. However, again, it doesn't matter how you do it. So this is going to be minus T1 cosine of 60 degrees plus T2 cosine of 40 degrees equals 0. You can plug them all in here too. T1 sine of 60 degrees plus T2 sine of 40 degrees minus mg equals 0. Okay, good. So, we actually know that T1's maximum is going to be 5,000 newtons. So we're just going to plug that in and actually solve for what T2 is. So, negative 5,000 newtons cosine of 60 degrees plus T2 cosine of 40 degrees equals 0. Well, the cosine of 60 is just the sine of 30. It's a half. So it'll be 5,000 times a half, which is 2,500 newtons, plus T2 cosine 40 degrees equals 0. Well, I'm going to move this over to the other side of the equals. So 2,500 newtons equals T2 cosine 40 degrees. I take T2 is 2,500 divided by cosine of 40 degrees equals, well, so I need to move to the scientific view. Let's do it right here. 2,500 divided by 40 cosine equals, okay, we got 3263 newtons. Okay. That's going to help a lot over here, isn't it? Because T1, now we're going to find mg, because T1 sine of 60 plus T2 sine of 40 is going to equal mg. Good. So we're going to take 5,000 sine of 60 degrees plus 3263 sine of 40 degrees. And that'll give us mg. We can solve for mass if we want, but we don't have to. This is going to be 5,000 times root 3 over 2, or 0.866. So that's going to be 4330 newtons. Because the sine of 60 is the cosine of 30, which is root 3 over 2. And this I really have to do on the calculator. 40 sine times 3263 gives us 2097 equals mg. We can add those together pretty easily. It's what, 27 plus another bump, which is 64 mg. Nice. Okay. That's an equilibrium problem. It shouldn't be too bad. Let's do some non-equilibrium problems next, and I'll make this the next video.